Welcome to the final round. You are sitting across from the lead architect in the interview room, and the pleasantries are over. Building a basic REST API proves you know the syntax. A senior candidate has to prove they understand the machinery operating underneath it. We are going to run through a rapid-fire technical drill. We will break down internal auto configuration, navigate transaction proxy traps, secure the endpoints, and prove your system is ready for production. These are the exact explanations you need to communicate your technical depth to a lead engineer. Let's start the simulation. Step 1. Internals. The architect asks how Springboot configures itself without explicit XML or manual bean definitions. The answer lies in the @enable auto configuration annotation. It triggers the Spring Factories loader, which scans your class path dependencies and conditionally wires the necessary beans. If the framework detects the Spring Data JPA library in the class path, it automatically builds the data source and entity manager. Next, they will ask why you prefer constructor injection over field injection. Constructor injection ensures required dependencies are provided exactly when created. By declaring those fields with the final keyword, you make the dependencies immutable and guarantee the object is always initialized in a valid state. This flowchart tracks how a request moves through the Spring MVC layer. The dispatcher servlet acts as the front controller. It receives the request, consults the handler mapping to find the correct controller method, executes your business logic, and routes the generated response back to the client. Walking through these routing and injection steps shows that you dictate how the framework operates, rather than relying on its default behavior. Now the interviewer shifts to object management. They want you to map out the exact life cycle of a Spring bean. This diagram tracks a bean sequence: instantiation, dependency injection, aware interfaces, bean post-processor, @post-construct, and finally, ready. By default, a singleton scope runs this once. A prototype scope triggers this entire sequence every single time the bean is requested. Tracking these precise states prevents silent memory leaks and ensures your initialization logic runs exactly when you need it to. Here is the classic transaction trap. Look at this side-by-side boundary comparison. The default required propagation forces an inner method to join the existing transaction, but requires new suspends the active transaction and creates a completely independent boundary. What happens if both methods use required? The inner method throws a runtime exception, but the outer method catches it. The error never propagates to the Spring AOP proxy. The proxy assumes success, so it commits the transaction anyway. To fix this, you have to bypass the default behavior. Inside that catch block, you manually invoke transaction aspect support.current transaction status.set rollback only to force the rollback. Next, they test database isolation. You need to explain that read committed prevents dirty reads, but still allows phantom reads, where new rows appear in subsequent queries. Serializable applies strict locks to prevent those phantom rows entirely, but at the cost of concurrency. Senior engineers must actively manage these proxy boundaries and database locks. Assuming the defaults will protect you leads to silent data corruption in production. The architect now pivots to infrastructure, asking how you secure the API and handle cross-origin requests. This sequential change shows the Spring security architecture. The request passes through a series of servlet filters before it ever reaches the dispatcher servlet. A custom authentication filter intercepts the request, extracts the JWT from the header, and passes it to the authentication provider for validation. Configure global CORS policies to define exactly which external domains are permitted to make pre-flight options requests, preventing unauthorized cross-origin resource sharing. For performance, optimize database interactions, tune Hikari CP connection pool settings, and implement Redis caching to offload expensive read-heavy operations. These performance tuning and security implementations are deliberate architectural choices made at the start of a project, not patches applied after deployment. The final phase of the interview tests your operational awareness, proving your application is safe to run in a live environment. You start by integrating Springboot Actuator, specifically exposing the health and metrics endpoints so operations teams can monitor the application state. But defaults are rarely enough. You stand out by explaining how to write a custom health indicator and use a meter registry to export metrics specifically tracking the uptime and latency of your external dependencies. You are showing that you build applications that actively communicate their health and failure states to the rest of the infrastructure. The simulation is over. You passed the drill. Junior developers recite the names of annotations and interfaces. Senior developers map out the internal life cycles and explain exactly what the framework is doing under the hood. Go back through these specific questions and practice delivering the answers out loud. Building that verbal muscle memory is the only way to communicate them clearly under pressure. Explaining these underlying mechanics proves you can manage the systems you build.